Today, we're going to talk about a relatively simple experiment that had huge repercussions for modern physics, the Michelson-Morley experiment. Back in the late 19th century, before Einstein's relativity and well before the rise of quantum mechanics, the most popular theory for how light propagates through space was that it travels through an invisible medium called the luminiferous ether. Michelson and Morley set out to prove the existence of this invisible medium, and the way they tried to do it was pretty ingenious.
But first, a bit of background. Edward Morley was a chemist, and he spent most of his life accurately measuring the composition of the atmosphere and the atomic weight of oxygen. So, each to their own. Albert Michelson, as well as being the second most famous physicist named Albert, was the first person to accurately measure the diameter of a star other than our Sun. He was also very interested in optics, and especially the problem of measuring the speed of light, which led to him becoming the first American to win a Nobel Prize in Science in 1907.
It seems like an odd thing to be fascinated by, but have you ever wondered where that 3 × 10⁸ meters per second figure comes from? One of the earlier ideas came from Galileo. He suggested you take two people and put them 1 mile apart from each other. Give each of them lanterns, but tell them to keep them covered at first. You tell person A to uncover their lantern so that person B can see its light, and tell person B to uncover their lantern as soon as they see the light from person A. There will be a time delay between the two people uncovering their lanterns, equal to the time taken for light to travel a mile. The idea was to have someone observing from a distance who would time this delay.
Unfortunately for Galileo, he would have found this time delay to be around 5 microseconds, which is 1,000 times shorter than the time it takes for a honeybee to flap its wings, which is of course a unit of time you should be very familiar with. This is basically imperceptible to the human eye and would have been absolutely impossible to measure in the 17th century. Later attempts to measure the speed of light used techniques to measure radiation from distant galaxies and clusters, and these actually got reasonably close. Then along came the French physicist Hippolyte Fizeau. He used a rotating mirror method, which Michelson and Morley actually used to more accurately measure the speed of light before their famous attempt to find the ether.
So, the ether. Although it sounds like science fiction, it was actually a pretty reasonable theory at the time, since physicists had no idea that light could travel through a vacuum. But it begs the question, why were physicists concerned with all this anyway? Well, the answer comes back to the speed of light. James Clerk Maxwell, famous for his equations that describe electromagnetism, found that light was an electromagnetic wave, and that its speed was equal to 1 over the square root of μ0 epsilon naught, both of which are universal constants.
What this meant was that the speed of light appeared to be constant. But given that this was before relativity, it made no sense for the speed of light not to depend on your frame of reference. But with the ether, we could theorize that Maxwell's speed of light was relative to the ether, which would be some universal stationary medium. It's important to note that the ether is stationary. This means that the Earth is moving relative to the ether, since the Earth moves through space as it orbits around the Sun.
This implies some sort of ether wind that, in theory, we could detect here on Earth, which is exactly what Michelson and Morley tried to do. Their setup was like this. There was a light source over here, and a half-silvered mirror here. A half-silvered mirror is basically a weird mirror that lets half of the light pass through, while reflecting the other half. This is why it's also called a beam splitter. The light gets split up so that it takes 2 different paths. So the first path goes like this, and the second path goes like this. These 2 things are just normal mirrors to reflect the light. They both end up here, at the detector. Both paths are exactly the same distance because the source, the 2 mirrors, and the detector are all the same distance away from the beam splitter. If we call that distance d, then you can check for yourself that both paths are exactly 4d long.
So how does any of this help them detect the ether wind? Well, let's assume that the wind is coming from this direction. Given that light travels within the ether, it would make sense for the light travelling in this direction to be faster than the light travelling along the other path. Since they travel the same distance, this means that there should be a time delay between the 2 beams of light reaching the detector, producing an interference pattern. This is why Michelson's earlier work on measuring the speed of light accurately was so important. They needed to be able to detect a tiny delay. In the end, even with all this accuracy, they were unable to detect a significant time difference between the two paths.
Now, the attentive viewers will probably have noticed that this experiment alone does not disprove the existence of the ether. What if the Earth just happened to be moving in such a way that there was no ether wind? Or maybe the ether wind just affected both paths equally? What Michelson and Morley did was repeat the experiment with different orientations and at different times of the day and year. This allowed them to account for any direction the ether wind might take, since the speed and direction of the Earth are always changing as it moves around in its orbit. And yet, they could never detect any significant time delay between the two paths of light arriving at the detector. This is why the Michelson-Morley experiment is sometimes called the greatest failed experiment of all time. They set out to find the ether, and instead, their findings supported a null hypothesis, making the experiment a big step in dismantling the idea of the ether.
But many within the scientific community still held on to this idea, coming up with more inventive ways to get around the negative result of this experiment. On the other hand, the evidence for the null hypothesis, that there was no ether, led to Fitzgerald, Lorentz, and later Einstein eventually developing the concept of relativity, revolutionizing physics and our wider understanding of the universe. But that's a subject for another video.
We personally would dispute the idea that Michelson and Morley failed. If anything, their experiment was a resounding success. Science is all about developing our understanding of why things happen, especially when it's not intentional. You can click here to watch our latest video and click here to subscribe. Thanks for watching.